You may recall the sample proportion was distributed. We first have to check for normality. We have to check that n times p times 1 minus p is greater than or equal to 10. The mean of it is just going to be the proportion, the population proportion. The standard deviation is going to be kind of this weird computation. It's not so bad if you think about it. Not so horrible if you really think about it, because a lot of that's just going to go into our calculators, especially all that square root business. So technically, your z-score calculation is going to look a little ugly. If you want to get down into the dirty nitty-gritty of it. Yeah, your z-score calculation won't exactly look pretty. P hat will be the supposed value of the sample proportion, whatever it is that we're testing. P is going to be the population proportion that we're testing it against, what we're assuming to be true. And then we're just going to have to make this standard deviation computation at the bottom. But this is almost identical, or it's virtually the same as when we did this z-score computation last time with x bar. Or even if you just do a z-score for a single observation. It's just take your statistic, you're in whatever data from the sample. In this case, this is just a single observation of the sample. In this case, this was the mean of your sample, x bar here. Take whatever the piece is from your sample, subtract off the similar value, but for the population, and divide by whatever the standard deviation is, or standard error. So it all looks nasty, but it's really not so bad. So let me pull up the homework. Let's just work a couple of the homework problems together. And you'll see that this homework is not so bad. It's not so bad, if you know that song. I don't know if you know that song. Okay, so describe the sampling distribution of p hat. Assume the size of the population is 30,000. There's a couple factors we'll take into account. Your sample size is 900. Your population standard, or your population proportion is going to be about 0.1. So technically what we want only a small percent of the population to be taken to be in the sample. So there's going to be a few things that we look at. First of all, we have to check the NP computation. NP times 1 minus P. We want that to be greater than or equal to 10. That's one of our normality assumptions for this section. N is 900. P is 0.1. 1 minus P is going to be 1 minus 0.1. And you can bust all that into a calculator. You can literally do 900, open your parenthesis, do 0.1, close parenthesis. Open another parenthesis, do 1 minus 0.1, close your parenthesis. And you'll get, let's see, you'll get 90 from here times 0.9, you'll get 81, which is surely greater than or equal to 10. So you get my seal of approval that first normality assumption is checked. Now, another normality assumption that we don't go into uber detail about because we're just not going to worry about it too much. But for the sake of this problem, what you want is you want your sample size to be less than or equal to 5% of your population size. So our population is 30,000. Our population is 30,000 strong. 5% of that, well, 30,000 times 0.05, it's going to be 1,500. Our sample size is less than or equal to 1,500. So this is going to be approximately normal because of part A, because our sample size is less than 5% of the population size, and this normality assumption that NP times 1 minus P is indeed greater than or equal to 10. So that's one we didn't talk about last time, was this whole, oh, well, your sample size has to be less than 5% of your population size. Don't worry about that so much. Just answer this question here. The mean of the sampling distribution, what the heck is that talking about? That's whenever it's time to sit down and calculate your z-scores, you have to have a mu, or you have to know what you're standardizing against. But we argued it's just the same as whatever the population one is, so 0.1. Now the standard deviation, well, let me clear the screen here. The standard deviation, that's going to be the square root of P times 1 minus P all over N, which is going to be the square root of P is 0.1, 1 minus 0.1 gets multiplied to that, all divided by 900. And so we can bust out our calculators. This one's probably not going to be so bad. 0.1 times 0.9 divided by 900. And we're going to take the square root of that bad boy. And it's actually going to come out to be a nice clean number, 0.01, which is super nice. This is going to be the denominator of any z-score calculations we do, which it looks like it doesn't even want us to do a z-score calculation on this problem. And we're done with it. Now, the $1 million question is, how do you know when to use which formula? Well, you just have to know if you're talking about a sample proportion and if you're trying to do inference on it, if you're trying to find probabilities concerning your sample proportion, then you are definitely going to want to use these formulas here. You're going to need to know what the standard deviation is, square root of P times 1 minus P over N. You're going to need to know what the mean of the distribution is. It's just going to be the exact same as the proportion of the population. And that's got to be just something that's provided to you. So P without the little hat on it is the population proportion, and it's generally got to be provided. P hat, the sample proportion, is usually what you're trying to do inference on. So you're going to suppose a value of P hat and then maybe standardize it as a z-score and so on. Are you provided these formulas on the next exam? Yes, you are. You will see if you go into the modules in Canvas, you will see that you will have the formula sheet for exam 4. It has chapters 7 and 8 formulas. It also has a very robust Z-chart. Let me tell you, it's the best Z-chart. It's the best Z-chart you're ever going to see. It's a big, beautiful Z-chart. So you will see those formulas. You can print them off and use them on your next exam. When is your next exam? Well, I'll be posting an announcement tomorrow on Canvas. But remember, if you consult the schedule, which is the uppity way of saying schedule, if you consult the schedule, you'll see that your next exam is going to be Thursday, next Wednesday, November the, the 18th, November the 18th. And in fact, you have a 2-day window to take it, the 17th and 18th. Or no, I have you guys just take it on the 18th. So yeah, your next exam is going to be next week. That means we're not meeting on Wednesday at all. You just take your exam during our time. We will meet Monday. So yeah, it's good stuff to know. Then fourth exam here covers chapters 7 and 8, which you may have noticed, maybe from doing the homework or something, chapters 7 and 8 seem a little bit light. They don't seem too bad. And that's, that's by design. We do it 2 chapters at a time. That last exam was a little bit meaty, was a little tough. This next exam, take it seriously, do your studying, but the next exam is going to be pretty doable, I think. It's usually the one that I see good grades on. So take that to heart. There also might just be an extra credit opportunity for the next exam concerning whether or not you choose to work the exam for review and get at least a 95 on it. So I'm thinking you guys should be checking your Canvas announcements sometime tomorrow. Certainly over the weekend, you'll get all the details you need for exam 4. So just keep that in mind. Just good stuff to know. Good old-fashioned good stuff to know. Okay, my computer's being wonky. Give me a second to adjust. There we go, back to it. So let's see, let's work another problem. No, I don't want to do that one. Here we go. Now let's really get our hands dirty here. Let's get our hands dirty. Suppose a simple random sample of size 50. So our sample size lowercase n is 50. Is obtained from a population that is 30,000 large. Capital N will be the population size. Lowercase n, the sample size. And whose population proportion with a specified characteristic is 0.4. So P, not P hat, P itself is 0.4. Again, that's for this section, that's got to be supplied to you. In reality, what we're doing is we're trying to do inference on that. So that's not in practice actually going to be supplied to you. We'll talk about how we deal with that later. But anywho, so we need to do a few of our normality assumption checking. First of all, the population size is 30,000. The sample size is only 50. The sample size needs to be less than or equal to 5% of the population size. Well, shoot, 5% of 30,000 is 1,500, and our sample size is way less than 1,500. So that normality assumption is good. Again, that's not one we go into uber detail on, but if it wasn't good, we wouldn't be able to do this problem. So you can probably guess it's going to be good on these last 2 problems here. The other normality assumption we have to check is this business being greater than or equal to 10. Well, lowercase n is 50. The proposed population proportion is 0.4. Then we multiply by 1 minus 0.4. We have to make sure that's greater than or equal to 10. Let's see if I can use my witchcraft here. Some of you may not know this, but I'm actually a wizard. That's not true. And please don't go telling people I think I'm a wizard. It's just a joke, because I like Harry Potter, whatever. So let's see. 0.24 times 50. Let's not use witchcraft, because I want to be exact. So 50 times 0.4 times 0.6 essentially is 12, which is very, very close. It's cutting it. It's cutting it close. But it does fulfill our other normality assumption, because 12 is greater than or equal to 10. But there's other textbooks, not this one, that say you got to be at least 15. So then it would fail normality assumptions on those textbooks. But that's okay. That's okay. We're good here. It's going to be approximately normal, because we verified that the sample size is less than 5% of the population size. And this other thing, n times p times 1 minus p has to be greater than or equal to 10. So we're good. So now we can actually start to calculate some of these statistics. And we can finally bring it all together and do some z-score calculations. Determine the mean of the sampling distribution of p hat. That's just going to be the same as p. Bada bing, bada boom. Determine the standard deviation, sigma. So it says sigma with a subscript of p hat. Oh, that's so complicated. It's just saying the standard deviation for this particular example. And it's just going to be that square root of P times 1 minus P all over N business. So it's the square root of 0.4 times 0.6 divided by 50, all of that in the square root. So we need to do 0.4 times 0.6 first, divide it by 50, then take the square root of that business, and we'll round it. It wants us to round to 6 decimal places. All right. There you go, 6 decimal places. Why does it want 6? Well, because it just needs a little extra TLC. I think its girlfriend broke up with it. And so it's feeling a little lonely right now, and it needs a little love. Okay, so suddenly, it's now asking us to do a z-score calculation and then find a probability. Now it's saying, what is the probability of obtaining 21 or more individuals with the characteristic? So out of 50, what's the probability that at least 21 will have whatever characteristic we're measuring? Well, that translates then to a p-hat of 0.42. What is the probability that in a sample of 50, at least 0.42 or 42% of the sample is going to have this characteristic? How do I know it's 0.42? Because 21 over 50 is 0.42. And remember, we're measuring a proportion. So we're looking for the probability that p-hat is greater than or equal to 0.42. Well, we need to standardize. We must standardize. Meaning we need to compute a z-score. The p-hat we use is 0.42. We subtract off the mean of this sampling distribution, which we already said was the 0.4 here, according to that formula we did. Then we need to divide by the standard deviation of this sampling distribution, which is what we just calculated here. All right, we're going to get a positive z-score. Pop this into your calculator, and we'll round our z-score to 2 decimal points. You should be getting 2.89. As your z-score. So we want to know the probability of seeing a z-score that is at least 2.89. That's what it boils down to. Well, we know how to do that. We need to go to our z table. We need to look up 2.89. So that's going to be all the way down here. And then there's no comfortable way of doing this. Now we can move it here. 2.8 and then go all the way down here. Here's 2.89. But remember, that's the probability of being less than or equal to our z-score. So we need to do 1 minus 0.9981. One minus 0.9981. So it's going to be very small. It's going to be 1 minus 0.9981 will be 0.0019, I believe. Hold on. To the left of the z-score. Okay. Why did you not like that then? Let me see if I may have actually calculated the z-score wrong. Oh, I was off by a decimal point. My mistake. I calculated the wrong z-score. You guys should have me locked up. I just literally put the decimal in the wrong place. It was just a transcription error. I apologize. So it was 0.289, which will round to 0.29 is the z-score. So I literally just, I don't know why, I just mentally saw the decimal point in a different place than it really was. Maybe you caught that when you were working through it. So it's going to be the probability of a z-score of at least 0.29. It's still going to have us do a 1 minus type probability. We go back to the z table and we look up 0.29. And here it is, 0.29, so 0.6141. So we actually got to do 1 minus 0.6141. Which according to my Mathemagic should be 0.3859. There we go. So yeah, just put the wrong z-score in. So then for this last one, you want to know the probability of getting p hat less than or equal to 0.32. So you would do this same computation over here, but you'd use 0.32, compute the z-score, and then find the probability of being less than that z-score using the z-chart. So you don't have to do the 1 minus trick on that one. And let's just go ahead and do it. The z-score in this case would be 0.32 minus the mean, which was 0.4, divided by the standard deviation, which I don't even remember what that was. It's out to 6 decimal places. It was 0.069282. So we do that computation. I can see it's going to be negative. Round it to 2 decimal points, it'll be negative 1.15. So now we want the probability of getting a z-score of less than or equal to negative 1.15. So we need to go to this z-chart that has the negative scores on it. Look up negative 1.15, negative 1.1. It's going to be this 0.1251. And we don't have to do 1 minus or anything because it's already a left-tailed or less than z-score. 0.1251. Hey. So really all this section is, okay, we're doing inference on a sample proportion. We just need to check some normality assumptions. Then we just need to know how to compute a z-score. So even though the formula looks different, it's the same z-score formula in spirit. Take the sample value, the sample statistic, subtract off the population parameter that you're interested in, divide by whatever your standard deviation is going to be. That's how you get your z-scores. Okay, so we've gotten a little bit ahead. We just finished chapter 8 there. And sometimes we can't help it. Excuse me. I always seem to have something in my throat. So if you hear weird sounds, it's usually me trying to clear my throat somehow. We got to jump into chapter 9. That's what we're going to do. I will send out another general reminder right now. Your next exam is going to be next Wednesday, November the 18th. You can take it. It will cover chapters 7 and 8. You can use a formula sheet. You can use scratch paper, but it has to be blank when you start off. You cannot come in armed with your own notes or anything. So no crib sheets, cheat sheets, whatever you want to call them. Not what we do. Remember, you are being monitored. And it looks like we're going to be using that honor lock again. So hopefully you have familiarized yourself with it. All right, so continuing on to chapter 9. Chapter 9 is actually going to be about something called a confidence interval. In fact, we saved the best for last. Kind of the two most important concepts in a basic statistics course, and really in the entirety of statistics, are confidence intervals, and even more importantly than that, something called hypothesis testing. Hypothesis testing is almost the entire point of statistics. You can run a hypothesis test for a lot of different things, and it's exactly what it sounds like. You're making a hypothesis and you're testing it using data and trying to decide if your hypothesis is valid, invalid, whatever you want it to be. You have to decide that using the data. So we're actually finally getting into like the heart of the matter, as Don Henley once sang about. So let's talk some chapter 9 material. You know who Don Henley is? Yeah, the Eagles, yep. Yep, him and Joe Walsh would sing for the Eagles. Anyways, so in chapter 9, we're going to start by talking about a point estimate. So here's what's happening. In reality, you have a population. It's usually so hilariously large. Now, you might want to measure something from the population. You might want to measure, how about the average blood pressure from the population? You know, whatever that systolic blood pressure number is. You might want to measure the proportion of all people who are going to be voting for a certain presidential candidate. Do you think that information is useful? Absolutely it is. You want to know what proportion of people in a state are going to vote for which candidate in a presidential election. Oh my goodness, isn't that polling information exactly what you see on the news for like the last 6 months up to the election? Even before that, they're constantly using polling information nonstop. And then you want to track polls, especially in some of the key swing states, like Pennsylvania was a key state this year, wasn't it? Georgia, Michigan was a key swing state this year. Swing just means we're not 100% sure it's going to go one way or the other. We know California is going to go Democrat. We know Texas is going to go Republican, or we're almost positive it is. But there are certain other states we don't know, and those are the ones that actually end up determining the election. So you absolutely would be interested in polling information and knowing what proportion of people are going to vote for a certain candidate. If you knew going in beforehand that candidate A was going to get 52% of the vote, you might suspect that they're going to win that state. However, it doesn't work like that. You think about the state of Pennsylvania, I think it collected, like 7 million votes or somewhere around there, or maybe less than that. That's 7 million people. You might only take a sample of 3,000 people, which is very small compared to the population it came from. Now, your sample of people might reveal that 52% or 0.52 of that sample will vote for the candidate that you're interested in learning about. But that doesn't mean the entire population will. So what we're doing, whenever we take a sample and we try to draw inference about the population, we're just using estimates. So the single point estimate for the population proportion is just going to be the sample proportion. You take a sample, way smaller than the population usually, and you count the number of successes or the number of things that go the way of whatever you're measuring and divide it by the sample size. For instance, if you took a sample of 1,000 people and 550 of them said that they were going to vote for candidate A, and I won't draw a name, I won't say actual names because people just get upset. If 550 people in the sample out of 1,000 people in the sample said that they were going to vote for candidate whoever, then the sample proportion is 0.55. If you do that math. It'll usually come out nastier. Usually it'll be like 553 over 1,013. which means you'll have to round your sample proportion. But that's the spirit of it. That's the proportion of people in the sample that are going to vote the way you want or have a certain characteristic. Now, does that mean in the population, 55% or 0.55 of the population will vote that way? It depends on how good your sample is. Almost certainly not exactly, but do you have a good estimate? Is it close? That depends on the sample size. That depends on your sampling technique. We all remember in the 2016 election, Hillary Clinton was supposed to win that election. You might remember everyone was like, oh, she's got this in a landslide. Did that happen? No, that did not happen. There's several key reasons that didn't happen. For one, the people that were being polled, there was actually a phenomenon called Trump shyness, where people, because there was so much kind of public shame or hate levied against Donald Trump, and this is not my opinion, this is just kind of how it was at the time, people would be afraid to say in a poll or to their friends and family that they're voting for Donald Trump. But when they get into the poll booth, no one is watching them, no one is knowing who they vote for. Could they actually then maybe vote for Donald Trump, even if they were too shy to say they could? Yes. Yes, they could. So it turns out we were not getting a fair sample of the population. There's some kind of error in the polling process. So that's why all those polls, one of the reasons why it just called that election wrong, completely wrong. And that's legitimately, if you look at, like, there's some major statistical publications out there, Pew Research, 538, they released some articles when the election came out, basically saying, hey, we were wrong, and they gave reasons, and that was one of the major reasons, was that people were not truly answering the poll in the manner that they would actually vote. That's an error, that's sampling error. So interesting stuff. In July of 2008, Quinnipiac, which I believe is a university in Canada, or perhaps France, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. So if we wanted to attain a point estimate for the proportion, so a point estimate for the proportion of registered voters who are in favor of the death penalty. This is just a sample. This is just a sample of 1,783 voters in the nation, and 1,123 said that they were in favor. So 1,123 out of 1,783 is going to be the sample proportion that has this characteristic. Now, that's almost certainly going to come out to be an ugly number. So we'll do the math, 1,123 divided by 1,783. Bust out your calculator. We'll round it to 3 decimal places, and it's going to be 0.630. And that's rounded. It was like 0.6289 or 6298 or something. So about 63% of the sample said that they were in favor of the death penalty. Okay, great. That means the entire nation is in favor of the death penalty, right? No. What if by random chance they only sampled people who lived in certain states where we just happen to know those people in those states are in favor of the death penalty? How do we know that this is a good snapshot of the entire US population, assuming that's the nation that we're talking about here? But is there any other nation other than the United States of America? I don't think so. All right, the United States is the best galaxy in the universe, all right? But anyway, so no, I mean, we could have random sampled from, a state where we just know that more people are in favor of the death penalty. We could have, accidentally sampled from a group of people who have had family members that were murdered, which is very sad. But you imagine that people who've had family members that were murdered generally are going to be a lot in favor of the death penalty because they have a personal stake in it. So if we had a disproportionate number of those people make it into our sample, then it's going to look differently than perhaps the entire US population feels about the issue. Those are all the problems we talked about back in chapter 1 and 2 concerning sampling errors, that you can't possibly get everybody in the entire population. And so you are making you're using a sample which is inherently just not as good. So how good is an estimate like that? Well, sometimes we don't like just a point estimate, a single value. Instead, it would be super nice if I could give you a range of values. If I could give you a range of values, and I could say, well, the true proportion of the population that is in favor of the death penalty falls between 48% and 69%. While that's a really large range, that gives me a little bit more clearer picture. Oh, well, actually, it could actually end up being a lot lower than we think, or could end up being a lot higher than you think. So a confidence interval is going to be something that gives us a range of values. It's an interval, exactly what it sounds like. An interval is just a lower value to an upper value. So let's look at some of the basic kind of terminology behind this. In a random sample of registered voters, 53% favor candidate A with a margin of error of 3%. What is the confidence interval? What we do is we take the point estimate, the 0.53 here, and we add the margin of error to it, and we subtract the margin of error from it. So you'll see this plus or minus business saying do both the addition and the subtraction. The low end will be 0.5, 0.53 minus 0.03 is 0.5. The high end will be 0.56, 0.53 plus 0.03 is 0.56. And so we're going to say that this is our confidence interval. This is exactly how we write it. We use parentheses on either end. We use a comma. And that is borrowed from algebra, kind of, in real numbers. And this is an interval of real numbers. And what we're saying is that the sample proportion, technically what we're saying is that the population proportion, we believe, is going to be in that range of values. It is an estimate, but it's an interval estimate. It's a range of values, which is just inherently going to have a higher chance of being accurate. You're much more likely that the true proportion of people who will vote for a candidate is going to fall within a range of values than just be a single value, 0.53. You're far more likely you're giving it some, wiggle room, if you will. So that 0.03 is going to be the margin of error. Now, the margin of error calculation will be different based on what exactly it is you're calculating. So let's go look at this. And now we have a whole heck of a lot of material we got to cover now to really bring up the possibility of a confidence interval. What goes into it? What are all the levers and things that go into a confidence interval? So first of all, we define a level of confidence. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. Oh, what in the world is that? That's double talk. You don't need double talk. You need blah, blah, blah. So, I don't know if you've ever heard of that name before. Bob, blah, blah. But anyways, that's just a joke. So the level of confidence, the normal level of confidence, the usual one you'll see is 95%. They'll say, calculate me a 95% confidence interval. You also might see a 90% confidence interval, a 99% confidence interval. You will not see a 100% confidence interval. The reason is that the confidence level tells me how confident I am that the true thing I'm trying to measure will fall in my range of values. If you have a 95% confidence interval, then I'm 95% confident that my range of values will contain the actual value I'm trying to do inference on, that I'm trying to figure out. Notice how in statistics, we're not coming out and saying, aha, the population parameter, the value we're trying to measure, will be exactly 52.1% or 0.521. It's never going to happen because you're inherently taking a sample. You're not doing the entire population until perhaps election day. Then on election day, that's when we're finally actually counting all the votes. Where technically, you're doing a census in each state. So inherently, because we're taking a sample, I'm not going to say it is definitely going to be this single value. What I instead am going to say, I'm going to be a little bit more delicate in my word choice. I'm going to say, I'm 95% confident that the true proportion of people who will vote for this candidate will fall between 0.5 and 0.56. Notice how, while that is almost kind of taking, it's not, I wouldn't call it the coward's way out. That's just me being extremely careful and safe that I don't try and nail down a specific value and say, he's definitely going to get 53% of the vote. Instead, I'm better off saying, well, I'm pretty sure, I'm 95% confident he's going to get anywhere from 0.5 to 0.56, or 50 to 56% of the votes go his way or her way. That's, while that does sound like just kind of, I don't know, it sounds dishonest, or it just sounds like you're just trying to cover your own butt. That is unfortunately just the nature of the situation. I can't make complete guaranteed 100% promises in this world. Now, if you wanted a 100% confidence interval for the proportion of people that will vote for a specific candidate, you want to be 100% sure that your interval will indeed contain the true proportion of people that will vote for that candidate. You want 100%, I'll give you 100%. I'm 100% confident that that candidate will get anywhere from 0 to 100% of the vote. That the proportion of votes they'll get is between 0 and 1. Thanks. That didn't tell me anything, did it? So a 100% confidence interval is worthless because it's got to completely run the range of all possible values. If you truly want to be 100% confident, in other words, it's useless. It's completely useless. I already knew that the lowest they could go is 0, the highest they could go is 100%. Duh. So you want a higher level of confidence, but you can only have it up to a certain point. And if you actually go too high, you have so much confidence and your range of values is going to be so much wider that it might be useless. Even a range of values like, well, I'm pretty sure he's going to get between 0.2 and 0.8 of the votes, 20 to 80% of the votes. That's useless too. I need it a little bit more narrow than that. I need you to kind of zoom in on that. So it's kind of a funny little paradox we have. We want more confidence, but the more confidence we get, the less interesting or the less useful the confidence interval is. So we actually dance along a really fine line in statistics when it comes to confidence intervals. And thus it's also a pretty interesting concept. So anyways, what we're going to say is that a 95% confidence interval, boy, that's the gold standard. But you can calculate a 90%, you can calculate a 99%, you could calculate a 50% confidence interval. You could calculate a 20% confidence interval. I guess in theory you can, but those are worthless. You want a confidence interval that's generally at least 90%, but no more than 99%. You can't have as much as you want. But 95% is considered the gold standard. We'll look at the formulas for calculating that. We have to look at something called our alpha. Our alpha, no, it's not just the little robot guy from Power Rangers. Alpha is going to be called the risk of a type 1 error. We won't go into uber detail about that until we hit hypothesis tests. But alpha is 0.05 if you have a 95% confidence interval. How do we know that? That's the proportion of confidence we're leaving on the table. So if you have 95% confidence, your alpha is 5% or 0.05. That's the amount of confidence we didn't get to snag. If your confidence is 99%, you left 1% on the table, so your alpha is 0.01. You express it as a decimal. Remember, if I say 97%, that's the same as 0.97. I can use those numbers interchangeably. So try not to get confused by it. So it's just the amount of confidence you're leaving on the table that you're not quite incorporating in your confidence interval. But it's kind of weird because we can't really talk about what alpha truly is until we get to hypothesis testing, and then it gets interesting. Okay, so remember all that song and dance we just did concerning the sampling distribution of p hat, which is the sample proportion, all that. Hey, it's going to come back here. We are going to build our confidence intervals. In order to do that, we have to have an underlying probability distribution. We have to have a distribution that we can do to actually make calculations, because otherwise I'm just pulling, things out of my head like, oh, I think it's going to be like 57%. Well, what am I basing that on? I can't just pull numbers out of nowhere. So what we need is a probability distribution, because probability distributions give us an idea of how certain things behave. We would love it. We would absolutely love it if the probability distribution we got to work with was the normal distribution, because then you can calculate z-scores, you can get probabilities from z-scores. There's all kinds of wonderful things you can do if you have normality. So for us to be able to use normality, we have to do a few of our checkers. We have to check our normality assumptions, but then we're going to use a lot of these same statistical values that we just computed in the last section, and we're going to flip them on their head and use them to construct confidence intervals. And since we already know the mean and sampling distribution and standard deviation of the sampling distribution of p hat, we're going to use all these formulas to construct our confidence intervals. So long story short, a confidence interval is going to be a formula you use. It's going to be a formula you use. And it's not a particularly pretty formula. It doesn't quite look as bad as you'd think. But basically, suppose that a simple random sample of size n is taken from a population. A 1 minus alpha times 100% confidence interval for the population proportion is given by this. This business here, p hat, is going to be the proportion of the sample proportion. This looks awfully a lot like our standard deviation calculation. In fact, that's exactly what it is. Now this z alpha over 2 is going to be a z-score that has alpha over 2 of the data to the left of it. How in the world do we find that z alpha over 2? What in the heck does it mean? Well, if you say wanted a 95% confidence interval, that means you want 95% of the data to fall in the very middle with Malcolm of the standard normal curve here. You want 95% of the middle. Remember, that's 0.95 if you put it as a decimal. We want our confidence interval. That means we want to cut off these tails here. The amount of data that's left for the tails, alpha, is going to be 0.05. That's going to be the amount we left on the table. So that means between this lower tail, the area in this lower tail, and the area in this upper tail, those have to add up to the 0.05 that's missing. But then because of symmetry, that means you got to split it in half. So that half goes into each tail. So actually, the proportion of the data in this tail is 0.025. The proportion of data in this tail is 0.025. And then to find the appropriate z-score, you need to look for a z-score on the chart that has 0.025 of the data to the right of it, which in turn means that 0.975 of the data is to the left of it. And that means we're going to have to use our Z chart. Oops. So we can use our Z chart. Let me pull one up here. And it is a little confusing. We'll work some problems next class on Monday. But basically, what we want to look on the Z chart. We want to find on the Z chart 0.975 inside of the chart as a probability. Oh, there it is, 0.975. In fact, we get to get it exactly. And that translates to a Z-score of 1.96. 1.96. So the Z-score that we're going to use here is 1.96. And that's going to be the Z-score that goes into our calculation. Once you figure that one out, that's actually the hardest part. Then it's just plugging things into a formula, use your calculator, and so on. All right, that's a good stopping point. Let me take attendance.